Okay, thank you. Maybe before starting my presentation, I'll provide my point of view on what you on the level answer the Peter's question. Standard access from compute nodes from Aurora to the external world allow only HTTP protocol. So if you want to access other protocols that will other protocols that will likely not work. So you need to make your communication either wrapped to HTTP packets or just limit your external world connection to HTTP protocol. Accessing any other like system calls will not be possible, unfortunately. So let me go back to the presentation. My name is Victor Anisimov. I'm a performance engineer at the Argonne Leadership Computing Facility. The topic of my talk today is Affinity in Aurora. Thanks to Chris for providing great introduction to the topic of Affinity. I can only say that Affinity is a very confusing name, if you heard it before, because the meaning of this word is very non-straightforward. So I'd like to start my presentation from some kind of disambiguation. According to Merriam-Webster dictionary, affinity is a tendency, attraction, or preference to something. You might agree with me that it's still not clear. But if you give yourself a time to think about those definitions, you may connect it eventually to what affinity means in HPC, what it means the shortest and the fastest path for data transfer. So when we talk about affinity, we are concerned about choosing the shortest and the most efficient data path for data transfer. We can have two types. We can speak loosely about two types of affinity: memory affinity and compute affinity. This is not very strict, but it's useful to do this type of analysis. Memory affinity is a proximity of a memory bank to a particular processing unit. This is also known as non-uniform memory access, or short for NUMA. NUMA deals with local and non-very local memory. Don't confuse the latter with remote distributed memory. Both local and non-local memory reside on the same node, but accessing data stored in local and non-local memory has different costs. So that's why we need to distinguish those. Compute affinity happens when we have multiple hosts, multiple CPUs, and multiple GPU devices in the node, like in case of Aurora. So then we need to be concerned about proximity of a particular device to a particular host. The degree of locality between units determines the efficiency of data transfer between memory and processing units. All that has also comes under the name NUMA architecture. So why NUMA architecture and where does it come from? Perhaps everyone would agree with me that the best computer is the one that has a single CPU, so it's easy to program, operated at a blazing speed, so it's infinitely fast, and equipped with vast and limited memory. Unfortunately, none of that is possible in reality. So we have to deal with modern compute nodes, which are increasingly parallel machines. Compute nodes in Aurora have multiple processors, multiple GPU accelerators, multiple memory units accompanying the processing units. And this architecture leads to non-uniform memory access, where the access to the memory from different paths have different costs. So the application programs must be highly parallel to utilize the advantage of NUMA architecture. So let's see what we have in the single node in Aurora. I'll have to repeat some of the Chris's talks, but I'll try to do that in a manner limited to the topic of affinity. So we have two socket configuration in Aurora now. Each socket has one CPU, 3 GPUs, and its own memory banks. And we have 2 sockets. In aggregate terms, we have 2 CPUs, 104 physical cores, each physical core is backed up with a compute unit, so they have computing floating point capacities, and those 104 physical cores are visible as 208 logical cores. We have staggering amount of memory, which is 1 terabyte of DDR memory on the node. In the node, 128 gigabytes of high bandwidth memory attached to the CPUs. We have 6 GPUs with 12 tiles, and again, staggering amount of 768 gigabytes of GPU memory in the node. All that leads to the outstanding double precision peak performance of Aurora node of 187 teraflops. These are amazing compute capabilities that will open the way to do new innovative science. We need to know how to properly use these resources. So let's consider an example of the aggregate memory. We have 1 terabyte of memory. So if you would like to use that memory in a naive way, in example 1, we launch one MPI rank that tries to allocate 1 terabyte of memory. It will fail. And the reason for that, because it exceeds the limit of 500 gigabytes of the memory bank assigned to a single CPU core. So it's an example of a NUMA architecture. So we want to correct this error and launch 2 MPI ranks, hoping that we can each allocating 512 will give us the aggregate 1 terabyte. But unfortunately, it also fails. And the reason for that is because both MPI ranks launched in the example shown in example 2 will land on a CPU 0. And as we know, CPU 0 has only 512 gigabyte memory bank. So requesting twice than that will fail. In the next example, we have 6 GPUs, 12 tiles. And so we want to, if we try to launch 6 MPI ranks to drive those 6 GPUs in the way shown in the example number 3, we will discover that the application is very slow. And the reason for that is because all 6 MPI ranks launched in the way shown in example 3 will unfortunately land on CPU 0. And the CPU 0 will be talking to GPU 3, GPU 4, and GPU 5 across the socket. And this type of communication is slow, so that's why we'd like to avoid it. So this speaks about importance of correct usage, knowing the correct usage. The correct usage requires the knowledge of how pieces interconnect. Let's review the Aurora node architecture. So we have 2 socket configuration. We have one CPU having 512 gigabyte memory bank and 64 gigabyte HBM memory. Each CPU is attached to 3 GPUs, and each GPU has 2 tiles. Each tile has its own 64 gigabytes of memory. Each tile can work as a mini GPU. So in overall, we want to minimize data transfer, to avoid data transfer between GPU tiles. We want to have 12 GPU tiles, and for that we need 12 MPI ranks to drive the computation. So this is the most common configuration in our Aurora nodes. So we use 12 MPI ranks per node. And as we learned from the previous failed examples, we need to avoid jam-packing the parallel tasks. Instead, we need to evenly distribute over the available computational resources. So let's see how to best assign 12 MPI ranks in the node. The most we'll begin the analysis from first learning how to assign or to bind CPU cores to MPI ranks. With 12 MPI ranks, we have 6 MPI ranks per CPU core. Each CPU, 6 MPI ranks per CPU. Each CPU has 52 physical cores. Each starting core, core 0 and core 52, are reserved for physical purposes, so they are not available for the user, so those are crossed out. You can see those crossed out. Those we cannot use. This leaves 51 CPU cores for the applications to use. With 6 MPI ranks, we can divide those CPU core resources evenly among 6 MPI ranks, and we get 8 CPU cores per 1 MPI rank. So each MPI rank can spawn 8 OpenMP threads. The CPU cores marked in the same color can be assigned or should be assigned to the same MPI rank. There is a very useful MPI exec option called CPU bind list. The example below the slide shows how to use this CPU bind list. In this example, physical cores 1 to 8 go to MPI rank 0. CPU cores 9 to 16 go to MPI rank 1. The next range from 17 to 24 go to MPI rank 2, and so forth. We can see that first and a column serves as a delimiter. We can see that 6 core ranges come from the CPU or socket 0, and another 6 core ranges come from the CPU 1 or socket 1. In this way, we get all 12 MPI ranks equally using all available CPU cores in the system. And the line with the MPI exec shows how to execute, how to do this binding, and how to launch your application, assigning 12 MPI ranks, each using 8 physical cores per MPI rank. Next to see is how to do a similar assignment using for the GPU tiles. Quickly returning back to the Aurora node configuration, we can see that I will quickly remind you that each PVC has 2 tiles, and so each tile has a separate 64 gigabytes of memory. And due to the connection that exists between specific GPUs to specific CPUs, you see here, each CPU connects to each 3 via PCIe Gen 5, which is quite fast. Another CPU connects to their own GPUs. And if we want to avoid cross-traffic, this is PCIe Gen 4, which is apparently between CPUs slower than PCIe Gen 5. So we have 12 GPU tiles. Each tile is a mini GPU. So we want to have 12 MPI ranks driving each of those MPI tiles, GPU tiles. In the previous slides, we already learned how to assign 8 CPU cores to MPI ranks using CPU bind list. As you see in this example, here I just reproduced the same CPU bind list as before. MPI exec also provides another useful option, GPU bind list, which can help binding GPU tiles to specific MPI ranks. We can use the format GPU ID dot tile ID here to address each GPU tile. Each GPU has a ID from 0 to 5. And inside each GPU, each tile has ID 0, or 1. So the format GPU ID dot tile ID allows MPI rank to directly talk to individual GPU tile. So here is an example. We use GPU assign GPU 0 and tile 0 to MPI rank 0, GPU 0 tile 1 to MPI rank 1, GPU 2 tile 0 to MPI rank 2, and so on. So we can see here, we have here 6 tiles. These 6 tiles binding to MPI ranks from 0 to 5, and CPU binding provides binding 8 CPU cores to the same MPI rank if we use this command, MPI exec, that launches CPU list, GPU binding list, and you start your application. In this way, we get MPI CPU resources like these 8 CPU cores talking to the corresponding GPU tile which reside on the same socket 0. So there is no cross-socket traffic that we wanted to avoid, and so on. So the CPU cores marked in the same color and the CPU cores and GPU tiles marked in the same color go to the same rank. So using this binding scheme, as shown here, we get with MPI exec, we get 6 MPI ranks allocating CPU resources and GPU resources residing on the same socket. So we don't accidentally get cross-socket traffic. And this is the most optimal configuration for data transfer when we need 12 MPI ranks and we want to have one GPU tile being driven by one MPI rank. This, we use GPU bind list to do the GPU binding. And there is a better way to bind MPI ranks to GPU tiles than using this MPI exec option GPU bind list. The reason is this MPI exec option GPU bind list has a limited portability and limited flexibility. To address that those problems, LCF has designed a wrapper script called GPU tile compact to bind 12 GPU tiles to 12 MPI ranks in the same way as we discussed in the previous title. This script is in the path, so it's available for everyone. The script works by setting environment variable Z affinity mask to each MPI rank. Here in this is a short summary of the script. The affinity mask uses the same format as we showed before, GPU ID dot tile ID, as it was in the previous slide. And this script, GPU tile compact, uses MPI rank in order to compute unique combination of GPU ID and tile ID. So each MPI rank gets gets exposed only to a single tile. So in this way, we get each GPU tile. In this computation, each GPU tile provides 64 gigabytes of memory. Consider another possible situation. Recall that PVC has a total of 128 gigabytes of memory on the device. And if your application, for some reason, needs more than 64 gigabytes of memory, the previous binding mode cannot accommodate that, but it can be done but it still can be done in PVC if we use a different mode, when application can access entire 120 gigabyte of continuous memory on GPU. So you don't need to do any specific efforts to distribute memory along to 64 gigabyte rank. The entire 128 gigabyte of memory becomes visible to the programmer as a single large memory bank, which is a huge memory capacity, and some application may indeed need that. So how to best assign these 6 MPI ranks to the 6 GPUs to the 6 MPI ranks and properly choose CPU core resources. The mode that PVC supports is when having 128 gigabyte of memory is called implicit scaling. The implicit scaling turns the GPU into a single device with 128 gigabytes of memory. The previous example that we discovered, that we reviewed using 12 MPI ranks and 1 tile, it's called explicit scaling, that it exposes 2 tiles with 64 gigabyte each. For quickly, the difference between implicit scaling and explicit scaling is just explicit scaling offers more flexibility and more potential for tuning, and potentially allows achieving somewhat better performance. On the other hand, implicit scaling is easier to use and provides more memory than the process running on a single tile. You may agree with me that rewriting the code that needs 128 gigabytes by means of using two tiles is quite difficult. So implicit scaling provides that convenience. Those applications that needs more than 64 gigabytes can simply use this implicit scaling mode. In this mode, we have 6 MPI ranks per node, 3 MPI ranks per socket because we have 3 GPUs. And if we divide GPU resources, we can use 16 CPU per ranks. Technically, we can use 17 because those that are still available, but 16 is most power of 2 is most common form of using compute resources. So this example provides this slide gives you example of using 16 cores per MPI rank, or you can use 17 if you follow the same recipe that we will be discussing. And we will have one full GPU dedicated to one full MPI rank. So we have LCF has developed wrapper script GPU dev compact to bind 6 full GPUs to 6 MPI ranks. And also it turns GPU into implicit scaling mode, so you don't have to do that by yourself. So we combine the GPU dev compact for binding GPU resources to MPI ranks with CPU binding list. CPU binding list to bind CPU core ranges to MPI ranks. Here we bind first 16 core ranges, 16 cores to the MPI rank 0, and so on, in the same way as we did before. By launching application with MPI exec shown here, we get 3 MPI ranks per node, and each MPI rank will be driving computation between 16 CPU cores and GPU residing on the same socket. You see, they're showed in the same color. By this way, we have these CPU cores communicating to their GPU only through the in-socket communication link, which is fast, and we avoid cross-socket communication like this. And this is my last slide that describes the most common uses, and I'd like to finalize my talk by sharing some final comments. So you could see from Chris's presentation and possibly also from some of my reviews of the Aurora single node configuration that Aurora node provide outstanding computational capabilities. These are 187 teraflops of double precision peak performance, 1 terabyte of RAM, and 768 gigabytes of GPU memory. It's perhaps you will not find any other leadership computing machine other than Aurora, which can provide so much memory to the researchers. Obviously, application programmers need to make their programs highly parallel in order to utilize all these outstanding computational resources. And you need to know Aurora node architecture. So you know how to properly bind CPU and GPU resources to MPI ranks. So you properly utilize the existing affinity between memory and compute units. You need to explicitly bind always CPU MPI ranks to physical cores to maximize the performance. And you need to use and recommended you should use LCF provided scripts for binding MPI ranks to GPUs because it's a little bit more complicated with the flexibility that provided available in PVC. You may also hear or learn while using further Aurora, that there are many more available binding options in Aurora, more detailed, more specific to particular uses. Unfortunately, those cannot be covered in the presentation because of short time. So you need to talk to your point of contact to discuss which binding option is the most optimal for your application. You can find more information about topic of affinity and binding in Aurora documentation following the provided link. And thank you very much for listening to this talk.